and the paper spends quite a bit of time talking about their verifier, right, which actually checks whether, for example, the program that you're about to run is actually type safe and everything points to the right place. And so we'll talk quite a bit about the verification. And so you might think about it, so the one question to ask immediately is, okay, why is these techniques useful, right? And what do they buy you? And it's sort of a little bit surprising because, again, what do they buy you? They buy you performance. In the following ways. Since everything is running in a single address space, thread switching is, for example, inexpensive. You can switch from two threads because they're basically user level. If you think about it, they're sort of like the user level thread package that you implemented in one of the homework assignments. And so the only thing you need to do is like switch some stack pointers around. You don't have to make a system call to the kernel. You don't have to change the process table, the CR3 register. Nothing of that. Right? It's just purely just a context switch. So that's cheap. In fact, there's a number of other things that are just very inexpensive. You can make fast system calls. Because everything's in a single address space and everything runs in the same CPL level, the privilege level, namely kernel level, right? Everything runs at CPL level 0. A system call is almost nothing else than just making a procedure call to another function. And so there's no int instruction that needs to be executed, and then an int interrupt that needs to be caught. The trap vectors that need to be set up, going through trap to deambiguate which particular system call it is. The system call is nothing else than just a procedure call. Call a method on that function, and that's it. And so that means there's a lot of the hardware costs associated with making system calls. You don't have to pay for them. Similar, they can get fast IPC in process communication because basically it's also a procedure call, right? To basically send a message from one thread to another thread. It all stays in the same address space. You stick it on the queue, you do a context switch, and the other guy picks it off the queue. So the communication costs are also low. And then finally, you can actually have applications. For example, those device drivers can actually have direct hardware access. Because everything runs in privilege level 0, every piece of code in principle can execute a privilege instruction. And so a device driver is also, even though it sits in the same address space, it sits in CPL 0, it can just interact directly with the hardware. And in a microkernel thing, that might be slightly more complicated depending on whether that's memory-based I/O or not. But you definitely don't have to make any system calls to get actually again to CPL level 0. So it's all cheap. And you might wonder, well, this is all great and well, but what does that have to do with robustness? It seems a story completely about performance. A programming language allows us to get basically all these great performance techniques. Right? Because the programming language, even though we're running in a single address space and we're all running at CPL 0, I will at least guarantee the borders between the different modules. And so what does this have to do with robustness? Why is this?
Perhaps because it cuts down the amount of code that you actually have to write. No IPC stack, no system calls per se, no complicated thread switching logic.
Oh, good. So you certainly you get some simplification in code writing. All the tricky code you would be writing about trap and all that stuff. You don't have to do it. So maybe from now on we should teach A2A in Singularity.
Too easy.
Yeah.
Especially if for allow you to just eliminate whole classes of bugs or whole classes of vulnerabilities.
So what allows you to?
So they mentioned at least buffer overruns just don't exist anymore.
Yeah. Yeah, okay, so there's certain things that the strongly typed thing that we're going to buy is that, because limitation, the verification techniques that, the restrictions they put on, like, for example, constructing and addressing with a process. But in the end, you get back, so you get some robustness back, but you get a ton of performance back. And you want to understand why. It's good to think about, like, so if you think back, what problem they were trying to solve, maybe there's one way to get at this, is they want fine-grained extensions. Right? They want, like, to take a big system, split up into smaller pieces, and have isolation between the different pieces. You can think about this in the context, say, for x86 or Linux, they want to take a process or a kernel, split the kernel up into different pieces while having good isolation. In the traditional microkernel designs, often this has been a problem because of the cost of IPC and the cost of thread switching and the cost of going entering into system calls. Right? Since they don't have to pay these costs, it becomes much more easy for them to actually split things apart. Right? Does that make sense? And so the right way to think about this is that these techniques allow you to basically take your web browser and chop it up to pieces and have extensions to your web browser run in a separate process. Because context switching to the separate process is actually cheap. IPC to that process is cheap, or relatively cheap. Correct? It's not free. But if you, for example, look at Figure 1 in the paper, the measure sort of the basic API call that's basically equivalent to system call. The measure of thread yielding, messaging, so ping-ponging back and forth between two processes, and the time to create a process. And in almost all cases, they're way faster than any of the alternative operating systems. Right? And the goal, and the thing that gets from this is basically this allows fine-grained isolation. Does that make sense? So in some sense, for the goal that they tried to set out to actually have fine-grained isolation, maybe hardware protection was not even the right thing to start with, right? Because it's just too heavyweight machinery to use for fine-grained extensions. Right? Okay, so what is the extension mechanism? We're looking from this perspective. What is the extension mechanism? And the extension mechanism is pretty simple, right? The story for what you do with an untrustworthy extension or a piece of code is that you run it as a separate process. Right? We call it isolated or sealed processes. And these processes are carefully, the word sealed is we'll talk a lot about this. These processes are very carefully constructed so that they basically can't really do any damage other than within the process themselves. Right? For example, they can't change over time. As you pointed out, you can't have dynamically linked coding to these processes. So the whole thing with DLLs is just ruled out because you can't do that. Once the process runs, it stays exactly the same way it is and is not modified. And so that's, so when you take an extension, you wrap it up in basically in a SIP, and it sits there and can't do really anything other, any damage it can do is only damage to itself. And the only way you can interact with a SIP is using IPC, or in their case, using channels.
Sorry, what does SIP stand for?
Sealed, isolated processes, if I remember correctly. But
Software isolated.
software isolated, yeah, I think it's sealed. They really care about the sealing aspect. Okay, and so this is going to come down back to this picture. They really wanted to go for this sort of full microkernel approach where you can take things and really split them apart into small modules, and then have the PL techniques that are guaranteed that there's hard isolation between them. Okay, so that's sort of the main background, and so the main goal that this project has. To be sure, this is the paper is pretty dense because it basically describes like 7 years of work, I think. in one document. So this is their overview document that describes the whole system. And almost of every aspect, of this design, there's another paper that describes just that one aspect in more detail. And so, as you read this paper, you have to sort of fill in a lot of the, read between the lines, what they're exactly trying to do, because there might be actually some other paper where they describe it in detail. And hopefully it's good enough to give you a good sense, how things fit together. Okay, so so what are the, if this is your extension mechanism, right, where you're only using processes or these isolated processes and channels, there's a number of challenges that you need to address that sort of guides most of the rest of their design. Talk a little bit about the challenges, and then we'll dive into how they do it. So the main challenges that we need to keep in mind is they want to make sure that they want to prevent buggy or malicious programs. From writing each other. Right, and actually reading. And this is sort of a standard isolation technique that we've seen many times over, but this time around, they want to do it without any hardware mechanisms. So how do you achieve sort of full hard isolation without any hardware isolation techniques? And the second thing that they care a lot about is they want to be able to clean up. So they want to clean and just clean it. And so when one process is, for example, misbehaving, they want to be able to shoot it down and guarantee that they get all the resources back, and there's sort of no dependency on any other things that, any other processes that might actually be affected by this. And so their whole goal, and this will show up in a bunch of different places, but this is an important thing to keep in mind as you're reading through the design of the paper and trying to understand why they're doing this. It always comes back to one of these two goals. Okay, so let's talk a little bit about the 3 key ideas they have to achieve these challenges. So the 3 big ideas. There's a lot of little ideas, but one is sort of first of all is this whole notion of a sealed process. The sealed process, once it runs, once you install it, then the process can actually make no modifications to itself. So they don't allow the process to generate code on the fly and insert that into its, whatever, in its process code base. The only thing, the way you can interact with the outside world is through IPC, and there's no other way to interact with it. It has its own garbage collector. So every process is one of the interesting things in this design. Every process in this type shape language has a garbage collector in it, but each process has its own garbage collector. And the reason for that is to make sure that all these processes are independent of each other. You want to be able to kill one process, including its garbage collector, and then they'll get the memory back. So they want to make sure that that garbage collector doesn't really is not managing any memory of any other process. And this is not the typical design of like a systems built in a type same language. Typically, there's one global garbage collector that manages all of physical memory. So they don't do that. And the reason is because we want this sort of complete, sealing off of the process. So then the second big idea they have is that their IPC is not sort of traditional IPC as we've seen sort of in labs 5, but they really have a sort of much more powerful sort of abstraction for it, which they call channels. And channels come with contracts. So to interact with another process, must be a contract that defines that interaction. In the contract, there are the same types are being used as in the rest of the programming language. And you can sort of, the system can just check that when one process does an IPC and passes some arguments, that these arguments are actually correct, and type check with the contract that actually is defined for that communication channel. The contract does also cover more things. They can even argue about how much buffer space is necessary to sort of facilitate communication between two SIPs. And the reason they don't care about that is because you worry if you couldn't argue about that maybe one process that is malicious could run sort of the kernel out of memory, and then you're still hoaxed, right? And so they want to make sure that a single SIP process can't actually sort of do a denial of service attack by allocating sending messages to one process continuously, and therefore taking a lot of memory up to buffer all those messages. And so we'll talk a little bit more about this. The contract helps them basically solving that particular problem. And then the third thing they have is something that they call manifest. And that is when they basically build the application. The manifest describes how to build the application. It describes all the libraries that application needs, all the resources that application needs. And before running the application, the system basically takes the manifest and basically creates a sealed process using the manifest. And so they don't allow dynamically linked libraries again, for the same sort of security reasons as before, for the robustness reasons, and the manifest will list all the libraries you need, and that's it. They claim they get an additional benefit from this, is that they can actually assign to programs principles. The security principles. Because the program can't change once it runs, it's basically safe to say, well, this program runs as a particular principle. Because over the lifetime of the program, there's like no way for the program to change its, the principle of which it runs. Okay? Okay, so far, any questions? All good? So what I'm going to do is just basically walk through these three ideas and sort of explore actually how they achieve them. Okay? All right. So let's start with these the SIPs. So the memory of a SIP is a collection of typed objects. So unlike, for example, in SV6 or in JOS, actually even the memory of SIP is actually of a process is not contiguous. You remember, because everything runs in a single address space, that would be very hard to arrange, that all the memory would be contiguous, right? Because they have no virtual memory to do remapping or anything like that. And so everything, gets allocated, and then somewhere in memory there's an object. And so you can think about physical memory, the objects of a SIP are sort of spread around in physical memory. They're not in any contiguous range or in a particular piece of physical memory. It could be all over the place. They have to do that because they have no mechanism. The virtual memory allows you to deal with fragmentation and all that kind of stuff, and they don't have any of that kind of mechanism. But that is a little bit dangerous, correct, in some sense, because since it's a single address space, in principle, if you didn't have type safety, you could basically address any memory location. Right? So they have to enforce rules to make sure that a processor SIP can't touch arbitrary, read or write arbitrary memory. Right? So they have two basic rules for this. You can only have pointers to your own data. so you cannot, have pointers, to objects that are actually owned by other SIPs or owned by the kernel. And so this allows, this is the sort of stepping stone to ensure that the SIP can read and write arbitrary memory, because the only arbitrary objects, the only objects that actually write are the ones that are owned by itself, and no other ones. There's a small extra complication, which is namely, when you do an IPC, you have to communicate some data, right? And they don't want to, in principle, you could copy all the data from one process to another process, but it can be expensive, right? And so, if you want to copy and send over something large, it would be a little bit painful to actually, send a big message and copy it over from one SIP to another SIP, because the whole goal was to actually have, fine-grained extensions, right? So we don't want to keep IPC costs low so that we can do direct interaction. So the way they solve that, right, is there's somewhere in the piece of the system there's something that they call the exchange heap. And objects can live in the exchange heap. So when a SIP, might actually have a pointer into an object that actually sits in the exchange heap. But they enforce a very, very strict rule for objects that are living in the exchange heap, namely with only one owner. So only one owner for exchange heap objects. And the idea is basically, for example, if the disk driver has a block that it has read, the block might be sitting in the exchange heap. The point that the disk driver did this action, the disk driver is the only process that actually has access to that particular object. When the disk driver sends it over a channel to the file system, as part of sending over, the ownership of that object changes from the disk, to the file system. So in fact, with object in exchange heap, actually with every object in the metadata of the object is basically listed who's the owner of that particular object. Okay? And so this enforces the rule that basically a SIP, with these two rules, it's impossible for a SIP to point to some object that actually another SIP actually owns. Right? So it gives you this strong isolation between the different processes. Okay? And we'll get more into the in a sec as we sort of figure out how the verification works. Now. Just to go back, right? So the collection of objects that a SIP actually owns is a bunch of code, right? The instructions that actually execute, plus the things that are sitting in the a bunch of variables that point to objects. And once you start a process, you can change the layout or anything, the structure of the process. You can insert new code, right? And this, one of the reasons they don't want to have this in the sealant is that maybe you can't do buffer overrun attacks, right? Or insert new code into SIPs or process because it's completely disallowed. You can't do it. There's no mechanism even for the SIP itself. It cannot actually generate code on the fly. Okay? At least they're going to enforce. You're going to have no code generation on the fly. So there's all this sort of class attacks that we read basically daily about. Right? In C programs, using buffer overruns or SQL injection attacks or all that kind of stuff. If it allows the attacker to insert code into the destination address space, it won't work in Singularity. Does that all make sense? Yeah, right.
Is that something that you can enforce on, just by looking at the assembled code?
Yeah, so we're going to talk about this in a second. How they enforce it. We'll go over it in a minute. But they do basically do that by using static verification. Right? This is the core idea of the verification is the key. Before they run the process, they go verify the process through the assembly instructions and see if there's any possible violations. And if there's a possible violation, they will run the process. so basically, when you think about a SIP, it's this collection of memory, and its instructions, and of course, there's a little bit of a trusted runtime that actually does some of the garbage collection and things like that in there. Right? And it actually is the only entity, or the kernel, that's the only entity that can cook up new pointers, that can allocate objects. The SIP itself can't actually allocate objects. It's only the runtime that can allocate objects. Okay, so if you think about this for a second, this is quite different from, like, say, a JVM, right? Or a Java virtual machine, where there's a whole bunch of different programs running in a single virtual machine. So what is shared in a JVM? Like, of course, Singularity has a single address space, so that is the same. What else is shared in a JVM? Okay, so the right way, the right answer is almost everything is shared. The right question to ask is, like, what is not shared? Because in the JVM, right, you're gonna, in a Java virtual machine, it is the case that one module can invoke, one procedure can invoke another procedure without any problems, right? Because there's no notion of really sealing things off. There's one global garbage collector, that manages all physical memory. So if one procedure does something bad and, like, runs out of memory, that could affect other processes running or other threads running in the JVM. So in a Java virtual machine, typically, and this is sort of the other sort of way of building, because we're like use C# or Java directly, and you would sort of build a type-safe system in it. You're still sharing one global runtime. You share the garbage collector. Basically, threads can interact with each other in many different mechanisms. Any sort of objects that are shared, like synchronization objects or things like that, are all shared. And this is all disallowed in the SIP world. In the SIP world, the only way in the two processes, two threads can interact is through IPC. Does that make sense? I'm harping a little bit on this because it's a quite different model than you might have encountered in the past. And so this makes a lot of things for them a lot simpler, right? Because it makes you can really cleanly kill a SIP in this world. Because in JVM, if you kill a thread, the thread actually has its fingers and all kinds of pieces in the sort of Java object space, and disentangling it from actually everything else that's sitting in the JVM is reasonable hard. In fact, the garbage collector has to go in and find out, like, all the objects that thread actually is able to access, garbage collect that, and it's a complicated process. In their world, it's very, very simple. Kill a SIP, and you know exactly which objects it owns, because it only points to its own objects, and it points only to objects that are. It's the only owner. If there's any object in the exchange heap that's owned by that SIP, it's only the only SIP that owns that object, and so you can just delete that object. And so the reasoning is straightforward. This all has to do with they want to be able to kill SIPs and guarantee they get everything back in the state without too much complications. Okay, so let's go through talk a little bit about the enforcement. How do you actually arrange this? And so the strawman plan, if you will, is you take your trustworthy compiler. Let's say whether you C# compiler, you Singularity compiler, you stick Singularity in as input, and an output comes from the center, correct? In the end, you have to run the code on the machine. So somewhere there has to be real machine instructions that are run, correct? And so one plan that you might think of doing, say, to get actual isolation, or to make sure that you basically enforce these two rules, is to take your compiler, put some source code in, the object code comes out, and you basically add to the object code a bunch of instrumentation. And the naive plan, which is just to make it very clear what the naive plan is, the naive plan would just take every load and store instruction and check, whatever address that load and store instruction is, reading or writing to, and we'll check whether that actually belongs to the thing that we're actually compiling, right? And the downside of that plan is there's two big downsides of that plan. One, it's expensive in runtime overhead, because every load and store instruction now needs to be instrumented, right? So that means like for every store instruction, there's going to be a check before the store instruction. After you compute the address, there's going to be a check saying, like, is this an address that this process actually is allowed to write? And if it is, then you go continue, and otherwise, you raise an error. Right? And so basically, every store instruction and every load instruction becomes a couple instructions. And so that just, and if that's in a loop, it's going to be hugely expensive. People try to go down this route, and there's also papers about how to sort of decrease the performance overhead for it. But even just doing it for pointers, that people do for C programming languages, even there, it's expensive. And they have to do it for every read and write instruction. So that's a bad. So there's a performance cost, that they don't want to really pay. The second thing is this pushes the compiler right in the trusted computing base. Because the compiler is the one that actually is going to ensure, the compiler has to ensure certain properties that then the instrumentation gets checked. And that puts the complete compiler in the trusted computing base. How big is a compiler? Is that a bit, how big is a compiler? So like a small little program, or is it like a gigantic program? How big is GCC? I actually don't know how many lines of code GCC is, but it's big. I mean, there's a lot of algorithms in it, there's a lot of complexity, a lot of phases, there's optimization passes. And so the fact it's a gigantic program, so it's likely that there's some bugs in compilers, right? And so you don't want to put the whole compiler in your trusted computing base. Particularly now that project like Singularity, where the whole goal was to sort of like isolate things very cleanly. Right? So they are doing a different approach than this, that avoids basically putting the compiler in the trusted computing base. And the way they go for it is by basically having a little verification module that really does is part of trusted computing base and does all the verification. So their approach is as follows. They have a compiler. Source language goes in, Singularity source language, and out comes this intermediate language, a bytecode, if you will. And you can think about this as a Java bytecode or any other bytecode. And then they have an installer, a program actually that runs, when you actually take the bytecode and actually want to turn it into and running as a process. And that process, that installer does two things. First of all, it runs a verification on the bytecode to double check, basically that these rules are actually adhered to. And once it gets the blessing, of it, then it actually turns it into compiles it to the machine code. And links it, with the trusted runtime. And the trusted runtime is the one that actually can allocate objects. Right? And it actually implements the garbage collection for that particular process. And so the idea is that that this box is much smaller than actually the compiler. I didn't draw it correctly. My boxes are the same. In fact, my eye is bigger than the C. I think. But really, the intent here is that the functionality that is implemented by the iBox is way simpler than the complete compiler. Right? And in particular, what is going to be important is that the verification is very simple. And so we can ask a bunch of questions about this particular structure. One thing you could do is you can imagine that actually you compile straight to machine code and you do the verification of machine code. What is our guess why they don't do that?
Because bytecode is more expressive, so it's probably easier to verify.
Yeah, bytecode is probably easier. There's two reasons I think they do this. Bytecode is indeed more expressive, contains more information, or they can put more information in it. which then they can verify. So that's one reason. The second reason is they don't have to do it for every hardware platform differently. Otherwise, you have to have a verification machine for every hardware platform. Another question you might ask is, so this module actually generates machine code. You probably know a lot of, it's like in JavaScript and Java, you often use just-in-time compilers, right? Just-in-time JITs. And so you generate code on the fly when the program is running. They decided not to do that. And why do you think they did that? Performance, although JITs are pretty efficient. And you just compile it. So the JIT, the overhead of JIT is not that large, right? You compile a piece of code once and then you run it hopefully many times. Yeah.
The jitter would also become part of the trusted computing base, and we want to keep the eyeballs.
Yeah, so the JIT would become part of the trusted computing base, and they don't want that, right? And furthermore, and remember, they wanted to seal the process off. And there's like no code generation whatsoever on the fly in SIS. So that doesn't really fit. Yeah, right.
Could you have a git generate bytecode and then use the same installer?
Yeah, so let me hold that question for a little. You can imagine, so I mean, the question here is, I think, could the machine code implement its own interpreter that could run then other programs that are constructed? Right? Let me talk a little bit about that. So why not verify compile time? Why verify installation time? The main reason for that is to put the compiler out of the trusted computing base. Right? Otherwise, the compiler would be part of the trusted computing base. And then I guess the final thing is, like, why not verify at runtime? You can imagine that you don't do the verification at installation time, but you do it while the program is running. And that suffers from the same problem as before as the strawman design, right? It's very expensive to do that. So it seems like the right place to do it. That make sense? Okay, so what does it mean, to follow these two rules? Right? I mean, like, what is the verifier supposed to check to make sure that these rules actually adhere to? So let's write that down and understand those, and then we'll give a little example to make it all super concrete. So what is the verifier need to check? So it needs to check that the code doesn't hook up any pointers. And that basically, the only, because that would be dangerous, correct? If an application could hook up its own pointer, it could make it point to something that maybe was not the intended thing that it was pointing to, and then you would be able to escape, sort of the type safety of the type safety system. And so the only thing that actually could hook up pointers is basically the trusted runtime. It can actually allocate new objects and return a pointer to the application. But the application itself can actually not hook up pointers. But at least the verifier has to check that the application can do that. The verifier has to check that or verify that the app doesn't change. Let me see if it's mind about the type. And so, in particular, we want to make sure that the application can't cast, a pointer from one type to a pointer from another type, because again, that will allow us, allow the application to escape the type system. Right? And in your code, and H8 and Lab, you do this all the time. Right? You're escaping, casting pointers left and right, and as you probably realize by now, it's pretty dangerous stuff. And so clearly, we don't want the application to allow it to do this, because you would totally be able to escape the type system. The verifier should also check that you don't use the object after freeing it. Again, we are sitting in a single address space, correct? And so it's probably likely, 1, 2, 3 an object that, the memory is being used, for another 6 objects. And so we could still scribble over it, we'd be pretty, be in bad shape. Right? And so the verifier has to double check that there's nothing happen. And finally, presumably the verifier needs to check. Don't use uninitialized variables. Because they might be pointing to things that that are incorrect or not type safe.
Shouldn't also check that you don't use objects that you've given up to the exchange?
Yeah, I think this is going to require. I'll talk. I'm going to skip. Let me skip the exchange heap for a second. And just forget about this, because even without the exchange heap, this problem is interesting to talk about. And then we'll add in the exchange heap as an extra complication that the verifier needs to deal with. For example, if you think about this, we're running a SIP, and the SIP doesn't communicate with anybody in any other SIP in the world, and it just sits there executing prime numbers or something. And we want to make sure that that even prime number program behaves correctly, right? It can't interfere with any other SIPs. It's good to separate these two. Okay, so clearly, I'm not gonna. The paper doesn't really describe, how this actually is done in any detail, right? It just says like there's a verifier, and it turns out, doing good verification is actually a little bit difficult. And so, let me give you one example of a program that you so you can imagine what the verifier sort of roughly has to be able to do. So, for example, you can imagine that there's this piece of intermediate, bytecode that, allocates some register R0, and this code does new of some particular type, so it assigns a type to that particular register. It jumps to L1. There's some other code after this, and then there's some code that actually R0 60,000, some maybe, and then it jumps to L1. And there's some other code in here, L1, and L1, what it does is, it doesn't move from whatever R0 is pointing to, content to where R0 is pointing to, it moves to the R1. Right, and so we can imagine that the verifier gets basically a bunch of bytecode like this, is looking at it and has to decide, whether this is a correct program or a bad program. Right? And clearly, if we're going, if we're running, if the program started here and then jumped to L1, this probably is an okay program, right? This is pointing to some variable, and we're basically taking dereferencing it and actually looking at the value and putting that in R1. However, if we were, the program in some way was able to get to this path to code, right? The second path, we're actually, R0 is sent to 0,000, and then we do dereference. Would that be good? No, it would not be good, right? Because we're dereferencing directly from physical address 1,000, and who knows what's in there, right? And so that's something we don't want to do. So you can imagine what the verifier needs to do is basically look at all possible code paths through the program and double check that basically all the registers and all the intermediate registers being used are type safe. Basically keep their type. Does that make sense? And I'm not gonna, this is just like a vague sketch about roughly how you can think about how this works. Basically, if you want to know this kind of stuff in detail, you take 6035 or something like that, right, where you really go into depth, doing program analysis. But there's a whole bunch of analysis basically necessary directly for these set of basically these double check these whatever the properties that I have somewhere on the board. These properties over here. That makes sense? Okay, good. So what is the, what are the benefits of having this verification? They're clearly, they're performance benefits, right? Because we don't have to stick in all the checks anymore, right? With this bytecode, we can verify, if we believe it's correct, and there's no bugs in the verifier, then, we can translate it into machine code if you run it. And so we don't have to put in all of these checks, before every load the store instruction. So that's clearly the benefit of the verification technique. Any other benefits? think of any other benefits. Yeah.
Like, I guess it's extensible, so you could change your verifier without worrying about what happens to the machine. Like, you put a new verifier in and all your old code still runs.
Good, yeah, certainly true. Yeah, there's a nice decoupling that they achieve by sort of pulling the verifier out of the compiler. Right? It can be totally two independent things. In fact, it can be, probably should be written by independent people and independent teams, right, to make sure that they are not making the same bugs and the same. The other thing I think the big advantage they get from this is that they can use the same verification techniques to actually check their IPC calls. Remember that the contracts actually have types in them too. That's going to be compiled down, and the verification at the level of actually make the construct the SIP. They can actually verify that the types that are actually being passed from the program to the IPC mechanism are also the correct. They correspond. There's no way of escaping it. There's a bunch of little small details they get. Because they can reason very carefully of the types and how big things are, because it's all sort of done by the static analysis verification technique. For example, they dynamically grow their stack. They do the allocated page for the stack, and then during sort of verification and runtime, they insert a little check whenever it risks that they run off the page, and then they allocate a new page. So their stacks are incredibly small to start with, and they grow as they use it. The reason they can do it is because they can so precisely reason about the structure and the execution paths of the program. This is sort of sitting like one sentence somewhere in the paper. So there's a bunch of other sort of little cool things like that that they get benefit from. All right. I think there's another small benefit they get. Unlike in x86 and unlike in Josh, when a thread actually enters the kernel, it actually runs in a different stack. Because we can't trust the user stack. And like we talk a lot about this, right? How about here? It isn't necessary when a process SIP makes a call to the kernel, which already is sort of a very different process than actually in x86 and Josh, because you're not really executing the system call, you're just executing the procedure call. It's important that we switch stacks. You can still imagine switching stacks, right? Or can we just keep running on the same stack? So what are the reasons that we switch stacks in x86 and in Josh?
Because the user process controls the ESP, so it can put that anywhere.
Yeah, basically we can't trust the user process, correct? They can do bad things to its stack, or put different things in the ESP, correct? We can't trust it. How about this?
Well, we still can't really prevent stack overflows from happening, right? And if there's no paging hardware enabled, then we won't be able to tell, right? So we might still clobber something, unless there's an additional check there.
So this dynamic page stack grow scheme that they have, make sure that the stack is always valid, and that you can run off your stack.
Then yeah, then you trust it.
Yeah, you can just trust it. Our verification machine basically ensures that whatever stack was used by the user program is actually a valid stack. And so they don't have to worry about this. In fact, so they don't switch stacks when they make a call to the kernel. They run in the same user stack. There's a bit of complication, which maybe I'll get to in a little bit, is that when you do garbage collection, you have to know when actually you enter the kernel, because you only want to garbage collect. The garbage collector for the user process will only garbage collect things that are actually on the SIPs, SIPs part of the stack, not the part that actually where the kernel is running on. So there's a little bit of complication, but in principle, you can actually run on a single stack. Does that make sense to people? You hopefully hammer home again how different this is than actually Josh and x86 are, right? And how much machinery actually Josh and x86 have to actually get isolation. Okay, good. So what is actually now the trusted computing base of this model? So we got rid of the compiler, but what is left?
Just installing.
the installer is certainly a big kind of part of the trusted computing base. And let me see, where's that picture? And of course the runtime. That should be the right trusted right there. Right? And so that's the other piece that actually the garbage collector, is in the runtime that hooks up the pointer, right? That allocates, there actually does memory allocation as part of the trusted computing base. Is that a question? All right. And so, in the kernel, of course, the kernel actually is in charge of, giving you pages of memory, and if the kernel does a wrong job about this and gives the same page to 2 different SIPs, then we have a problem, right? So the kernel will be still part of the trusted computing base. Okay, good. So, so let's now talk about the exchange heap. And so we'll need to go through this, right? The exchange heap is this idea that where objects can actually, pass, from one process to another process. And so there's some additional mechanism necessary to make sure that everything works out correctly, right? That the verification that we've done is not violated by the IPC system. That's it. So what are the way this works is blow this up a little bit. So exchange heap. So there's a channel which points to an endpoint. An endpoint is just an object that actually lives on the exchange heap, in the exchange heap, and that actually has a queue of messages, which are basically also some type in this particular programming language. And so when a process, and the rule is that there's only one owner for every object on the exchange heap. Right? And in this particular case, this process actually owns this endpoint, and that owner points to one other message, and that points to one other message. There's never a case where there's 2 pointers to the same object in the exchange heap. They basically ensure that this rule is followed, or they want to ensure that this rule is followed. So there's a bunch of dangers that you need to think through, right, if you have a mechanism where you can hand off objects from one process to another process. And one of the things you got to make sure is that if you say, so the sender, let's assume that this is the receiver, and so somebody else, like the file system, was the sender. So the file system puts some object, some type of this queue. You got to make sure that the disk will interpret that object exactly with the same type, right? And that they things line up. Because otherwise we would have, again, a big problem. And so the way that happens is through these contracts, where the contracts specify the types that actually can be passed into an IPC. And so the sender, the verification mechanism checks that the sender only produces objects that actually match the contract types. And the verification machinery also checks that the receiver only accepts or only uses objects that match the contract type. Does that make sense? So there's no way of confusing any objects in the exchange heap, when they hand it off from one process to another. Another danger that you have to be careful about is if the file system sent this message to the disk, we're going to make sure that once the disk gets it, that the file system can't actually scribble over it anymore. And how is that done? Or how would you imagine doing that? Working a rule like that.
Once you call the trusted runtime saying, hey, exchange, you can have this object and transfer it to another, you never access it again.
Yeah, so the verifier needs to check, like when there's a call to send, basically, that passes in some object, like some R0, and then the verifier knows, at that point, the sender is not the owner of the object anymore, and it should check that after the send, the sender doesn't use that object anymore. Or the verification machinery has to check that. Right? And so this is all part of this, if you will, this static analysis or this analysis tool that sort of verifies what actually happens with the types of variables. Okay, that makes sense. So that at least excludes that danger. And the verifier already has to be able to do that, right? Because the application is allowed to delete objects, and so the verifier has to check that also after the deleted object, that you don't use it anymore. And this is almost the same thing. Instead of deleting, you're actually handing it off to another SIP. Okay, then there's another problem that that they want to make sure that it avoids that they want to avoid is that if you're not very careful, the file server just can keep sending messages to the disk, right? And so basically, this queue is going to grow, and then you run out the kernel out of memory or the machine out of memory. What is it that how would you solve? What is it in Singularity that actually ensures that it doesn't happen? Anybody remember from reading the paper? Again, it's sort of buried in one paragraph. One of the many ideas they have. Yeah.
Can you say something about one cycle you have to send and receive call?
Yeah. So they force a rule that after a send call has to be followed. So in the contracts, the contracts specify the types, but they also specify more or less the interaction between the sender and the receiver. And every contract has to be written in a way that basically every send is followed by a receive. And so basically this assures that any SIP can, in essence, have only one outstanding message to any other SIP. And they cannot send a second one because that would violate the contract and actually the program would reject it and would not even run. Make sense? So you can see that actually they use this verification technique in pretty powerful ways, not just to analyze a single sort of bag of instructions, but also the interaction between two different processes and like the communication channels. Okay, so the contracts basically check these. Allow the system, the existence of contracts allows the system to check that the types of objects exchanged for the heap don't change right, between the sender and receiver. It allows to check that the queues are finite between sender and receiver. And it does it even catches some protocol bugs, like when you send a message to a device driver that hasn't initialized yet. Because the contract actually has sort of a state machine that sort of describes what happens to the state of that driver, of that process after each message that is being received. And so, in fact, you can even argue about some protocol bugs that you might have between two processes. Okay, this is exciting. You guys are very passive today. Like, all looking and sounds reasonable, or boring, or I don't know exactly what you're thinking, but yeah.
First Monday in 2 weeks.
The first Monday in 2 weeks. That's it. I'm hoping that was a pretty exciting thing because it's like so different from what you've seen. Okay, so continuing then. It will be a fast lecture, and you're out of here. So let's, we typically don't really look at the evaluations of these papers, but this one is sort of interesting to actually take a quick peek at. So if you, I don't know if you looked at figure 4 and figure 5, which are these bar graphs that show performance numbers. And the first thing that I want to ask, the first thing, while reading the paper, the whole goal, correct, of this system was to actually get better robustness. Is that evaluated anywhere in the paper?
If we accept that more performance code lets it be more robust, then yeah. But otherwise, I think basically just like, yeah, well, we need to put it into practice, so on time we can do that.
Yeah. So basically, like the main claim of the paper is, if you take a sort of aggressive view on whether they deliver on their goals, then you should have to say, well, they don't, right? Because they haven't demonstrate that this design is more robust than the other designs, right? And that's just there's nothing really bad about this paper. Most papers don't deliver on their goals. But they make an attempt to get their goals. But it's always careful, like when you're reading the evaluation section of any paper, the first question you should ask is, okay, what are the original goals of this paper? Right? You go back to the introduction and it says something, oh, we're going to solve the world's biggest problems, correct? And then you can go back to the evaluation section and you double check, that there actually is a graph that actually corresponds to whatever claim they made in the intro. And this paper, as many other papers, has a claim in the intro that where no corresponding graphs were. And so if you're a hard-nosed, research scientist, you say failure. Yeah. But again, so similar. Then coming back to your point, do they demonstrate that this is a good model for extensions? You mentioned other models for extensions, right? In fact, I've used other models for extensions, like dynamic link libraries, plugins, and all that kind of stuff. And in many ways, they've been arguing in this paper that this is a good way of making your extensions more robust. And again, there's no validation that demonstrates that this is a good model for extensions, right? Because they didn't write many extensions. And they wrote, a few extensions, and for those few, it seemed good. But, that's not, if you're a hard-nosed scientist, that's presumably not a sort of very completely convincing argument, correct? They find 2 extensions for which, they could write them. That's great. But how about all the others where, there's no real validation about how good they could do. Now, of course, it's hard to figure out how to do that, right? Like, how do you measure robustness? How do you measure, whether a programming model is good for extensions? It's not so easy. Yeah, go ahead.
That was my question.
Yeah. So how do you measure that?
Well, okay, so maybe a question that I really want to ask is it ever expected that you should get, a giant cohort of software engineers to start using your system and see how they like it, or see how much more practice?
That'd be the ideal thing, right? I mean, the ideal scenario is, you actually deploy the system for 10 years, and then you write an experience paper afterwards saying, yeah, it worked exactly as we predicted it would. And that typically doesn't happen. So I'm saying it's almost unreasonable what you're asking for, but there's certain things you can do to sort of get a better handle on it. Right? So typically what people do with robustness often is they inject faults. They sort of think about, okay, what would be possible faults you could inject? Right? Like there's certain faults you can't even not inject with Singularity because that'd be unfair. Like for example, you could inject a flaky verifier. That'd be unfair to do. But you can imagine like all kinds of other things you could. Sort of attacks or faults that are within the scope of Singularity and see actually if they work correctly. And that's a typical thing that people often do. If they do a good robustness paper, that's something they do. Or random failures or something. You try to do something, they clearly didn't do anything. Similarly, for extensions, the way you go about it is you presumably say like, well, extensions, some extensions you need this, some extensions you need that, some extensions you need that, and these types of extensions exist. And like we can support them all, following the following reasoning. Or we wrote one class, and therefore we have sort of some confidence that this actually is the right model. And so you might ask, like, why did you assign this paper? If you don't believe the evaluation section, I think the paper is by itself an interesting design. Period. So even without sort of hard-nosed, high-quality evaluation, it's an interesting paper to read. And particularly in 828, where we spent 10 weeks or 9 weeks only thinking about isolation through page tables and CPL and all that stuff. And I wanted to make sure that you understand that there's another way of doing business too. Right? Although this way of doing business that hasn't demonstrated that it is better than the CPL approach, correct, or the page table approach that you have been implementing. Okay, so what do they demonstrate? They actually demonstrate some interesting things. They mostly do performance evaluations, and that comes back to an earlier point, correct? Their belief is you get good performance in these neighborhood, in these areas, then you actually allow fine-grained extensions. And so they more or less delivered already that in table 1. The other thing they deliver on is they look at other isolation mechanisms and measure the overhead for that. And they are in a unique position to do that, right? Because you couldn't turn, like in x86 or in JOS, you can't turn off isolation, right? And then measure the cost of it. It's very hard to do because your operating system is not written for it, right? And you want to get for instruction 30, you would be a problem, right? Assuming turning on the hardware page table was essential to run your whole system, so you can't turn it off. The whole thing won't work. Mm-hmm. But they can play games. And so one of the things they do actually is they, in addition, they set it up in a way that actually they can actually add hardware isolation. They can take actually every SIP and run every SIP in its own address space. And basically measure the cost, for doing that, and that would sort of reflect the cost that you would have for a system that is sort of microkernel based, like a true microkernel where everything runs in a separate hardware protection domain, right? And so if you look, so if you look in this figure, so the most interesting figure in this is figure 5 in this paper. The first thing, actually, the first thing they do is actually they turn off all their checks in their so the compiler generates the verifier, the compiler generates checks. The verifier checks if these checks are there. For example, you have to check like array bounds to make sure that the program doesn't get outside of its array. And so they turn it all off. And they're basically saying, well, that is basically the most unreliable world, correct? And if you add those runtime checks back in, then you get basically what Singularity has. And so if you look at that, they call this the safe code tax. So like, how much do you pay for just having isolation enforced by the programming language? And so they took one benchmark, a web file benchmark that basically reads and writes files or serves files over a web server connection. So the experiment is you have basically a NIC SIP, a TCP SIP, which includes a little web server. You have a NIC card, and you're basically sending and receiving small web pages. And they measure that without any checks in the binaries for Singularity, and they observe basically you're paying sort of like 5% overhead in that benchmark for just having types, for getting isolation through the Singularity mechanism. And then they basically go and then they turn on hardware page tables. Right? And hardware tables starts turning on this isolation mechanism. And so that turns on the TOB, and so there are all kinds of costs associated with actually using the TOB in hardware page tables. And basically, they can measure that. And in fact, the first thing they do is they run one experiment. They run all the SIPs in the kernel, but with virtual memory turned on. So it's one virtual address space instead of one physical address space. Right? And so that actually costs about 6% of performance, over 6% slower than sort of pure Singularity. And then the next thing they do is they actually run every SIP in a different address space. Right? And so that means that when you do a kernel call, you do actually you have to switch page tables, all the machinery that basically x86 or JOS uses, correct? And then you get basically sorry. They just put everything in a separate protection domain, not in a separate. So there's still everything is a CPL 0, but they have different page tables for every SIP, and that gets you to 18% cost. And then they add the kernel in, and then you get sort of in the roughly 33% overhead. And so their argument is that like our way of doing business, for fine-grained extensions is a much better way of doing it because like look, if you didn't do it that way, if you use hardware mechanism, 1/3 of your performance is lost. So this comes a little bit at the same question earlier, like, is this a good model for extensions? And they would argue yes, because the performance over cost of making an extension is so low that this is the right way of doing things. So it's a very indirect manner of arguing that this is a good model for extensions. Yeah, go ahead.
Why would having a single virtual address space instead of just physical memory add any overhead?
Because like for example, you have a TOB and you got TOB misses. The TOB contains a cache of the recent translation from virtual to physical addresses. Right? The TOB is small. In fact, the TOB is quite small in x86. And so if you have a big address space and you're running around a lot in address space, you're going to take TOB misses. And so that's what one cost that you can get. And one of the things that is cool about this paper is that you can actually tease apart, for that particular benchmark, those different costs. Right? Yeah.
But if you did your extensions in a DLL format or some other, space where you weren't doing the microterminal design, you wouldn't take the 33% hit.
No, but then you wouldn't get the robustness. Right? Because if you were just linking DLL with your application, then you would get no robustness. So in fact, they would argue that like the robustness, the safe code text that pays only 5%. And so over an approach that just are purely DLLs and there's no safety, the only win you're going to get against them is 5%. And so they're arguing, well, that's fine. Right? I mean, like, wouldn't you be happy to have a very robust system for only 5% performance overhead? Now, there's a couple of restrictions, right? You have to write in C#, and there's no other programming language you're allowed to write, allowed to use. But if you're willing to buy into that world, then basically you pay 5% and that's it. Yeah.
Is there really a way to make it viable for apps that could be used, like, that use JITs or anything like that?
Sorry?
Is there a way to make it viable for apps that people use that have some time compilers or?
Yeah, it's an interesting question, right? Like, could you have like an interpreter sort of inside of the? You cannot have a JIT inside of the SIP, right? Because that would violate, the code generation stuff on the fly. You certainly could have a little interpreter inside, and the verification machine will check that the interpreter doesn't do any bad stuff, right? That's okay. But no, in real JIT, we can try.
So it's just don't try it with this, so it's.
Yeah, you can't do it with this OS. It's just, they really come from this perspective, okay, well, you really want to tackle the robustness problem. That's paramount you do. Okay, I hope that was a little bit exciting then. I mean, it is really I find it a pretty interesting system because it's such a different way of thinking about it than we normally do. All right, on Wednesday we have a totally different topic. Also very exciting.